Welcome to lecture 45 on essentials of topology. In this lecture 2, we will study the concept of path connectedness. In the previous lecture, we have already seen the possible relationship between connectedness and path connectedness. We have also studied a number of results related to connected topological spaces. Even connectedness doesn't imply path connectedness. We will study some of the results related to path connectedness of a topological space which are similar to the same in case of connected topological spaces. Begin with the first one. We have already studied such theorem in the case of connected topological spaces. The statement of this theorem is that if X tau is a topological space and this is a collection of path connected subsets of X satisfying that their intersection is non-empty, then union of EI, I belongs to I, is path connected. In order to justify it, let us begin with as this intersection I belongs to I, EI is non-empty. We can take an element in this one. Let us fix this element, that is X naught belongs to this intersection. Also, let us take this union of EI, I belongs to I, as a set E. Our motive is to show that this set is path connected, and if we want to show that this is path connected, so let us take two elements in this set, that is X and Y belongs to E. And if X and Y are elements of E, one of the possibilities is that this X and Y belongs to EI for some I in I. If they are lying in same subset, which is EI, and EI is path connected, we can always find a path from X to Y. So what we are considering as this E is union of EI's. So let us take X belongs to some EJ and this Y belongs to some EK for some different J and K in I. It is to be noted that this EJ and EK are path connected, that is EJ and EK are path connected, and the fact that if X belongs to EJ, note that X naught also belongs to EJ. It means that X naught and X are elements of EJ, and this X naught and Y are elements of EK. If X naught and X are elements of EJ, there exists a continuous function. Let us take this is P1 from this closed interval 0 1 to EJ, satisfying P0 is equal to, we are taking this is X and we are taking P1, this is actually P10, this is P11, that is equal to X naught. Note that this P1 is a continuous function. Similarly, there exists a continuous function P2 from this closed interval 0 1 to, let us take this is EK, such that this P2 0 is equal to X naught and P2 1 is equal to Y. So what we have shown here, that if we are taking this set E, that is union of all these EI's, so what is happening here, that if we are taking any XY in this E, this is X and Y, what is happening if we are taking this is X naught, there exists some path from X to X naught, and also there exists a path from X naught to Y. So use the construction based on pumping lemma which we have already studied in the previous lecture, what we can deduce that for all this xy belongs to E, what is happening? There exists a continuous function, and this continuous function is given by P, that is from 0 1 to E, such that P0 is equal to x and this P1 is equal to y. It is to be noted here that I am not providing the details about this continuous function P, because this construction we have already done in the previous lecture. Thus, what we can say that for each x and y there exists a path, and hence this E is also path connected. So that's the proof of this theorem. Moving ahead, let us take another theorem. Again, this is similar to the concept of connected topological spaces. Continuous image of a path connected topological space is path connected. In order to justify it, what we have to show that, let us take a continuous function f from a topological space x tau to y tau dash. This function is given that this is continuous and this x tau is path connected. What we have to justify that, this fx with relative topology, this is path connected. Now, in order to justify it that this is path connected, let us take two elements in fx. So what we are taking y1, y2 in fx, and our motive is to justify that there exists a path. In order to construct the path as y1, y2 belong to fx, obviously there exists some x1 and x2 in x such that we can conclude that f of x1 is equal to y1 and f of x2 is equal to y2. Also, note that this x1 and x2 are in x, and what this x is? This x is path connected. And if this is path connected, we can construct a function. This continuous function is p from 0 1 to x such that this p0 is equal to x1 and p1 is equal to x2. So finally, what we have with us, this is the space x, and let us take this is y. What we have, this fx is included in this y, that is this is our x, this is y, and this is f of x. We have taken two elements y1 and y2 in fx. Corresponding to y1 and y2, we have chosen x1 and x2 in x such that f of x1 is equal to y1 and f of x2 is equal to y2. That is, this function is f, this is our y1 and this is y2. Also, what we have done, we have taken an interval. Let us take that this is 0 1, and what we have shown that this p0 is equal to x1 and p1 is equal to x2. So this is the function p sending 0 to x1 and 1 to x2. Now from this picture it is clear that we can construct a path from this closed interval 0 1 to fx. Question is how? Answer is here. Let us take a function p dash from this closed interval 0 1 to y, which is defined as composition of f and p. Note that f is a continuous function, p is also a continuous function. Therefore, p dash is also a continuous function. Question is, what about this p dash 0? That is composition of f and p at 0, that is f of p0. Note that p0 is x1, so that is f of x1, or this is y1. Similarly, we are talking about p dash 1, that is f composition p at 1, that is f of p1, that is nothing but f of x2, and that is y2. Thus, there exists a path from y1 or a path connecting y1 and y2, and therefore f of x is path connected. Moving ahead, let us use this result, and by using this result we can conclude this simple result. The statement of this theorem is that quotient space of a path connected topological space is path connected. Just recall the concept of path connected, or recall the concept of quotient spaces. What we have studied, that if a topological space x tau is given, and let us take this is a quotient map. This is a map from this A with having quotient topology on it. If this space is path connected, we know that this Q is a continuous surjective function, and therefore by using the previous result, what we can say that this space is nothing but a continuous image of this path connected topological space, and therefore this space, that is a tau q, is path connected. That is, quotient space of a path connected topological space is path connected. Even one more result we can deduce from the previous one, and that is path connectedness is a topological property. Just recall the concept of homeomorphism. It's simple to deduce. Moving ahead, let us discuss the path connectedness of the product space. Again, this result is similar to the result that we have studied for connected topological spaces. So, let us take two topological spaces x1 tau 1 and x2 tau 2. Both are path connected topological spaces. What we can justify that the product space, this one, that is x1 cross x2 with product topology, is also path connected. In order to justify that this space is path connected, let us take two elements of x1 cross x2. So what we are taking? We are taking the first element, let us take x1 x2, and second one is x1 prime x2 prime, or x1 dash x2 dash in x1 cross x2. Our motive is to justify that there exists a path connecting this point x1 x2 to this point, that is x1 dash x2 dash. When we are taking these points in x1 cross x2, what we can conclude from here, that x1 x1 dash both are elements of x1, and x2 x2 dash both are elements of x2. Again, it is to be noted that x1 and x2, that is x1 with this topology tau 1 and x2 with this topology tau 2, both are path connected. And if both are path connected, we can construct some path from, that is some path connecting x1 and x1 dash and a path connecting x2 and x2 dash. So let us take this function, that is a continuous function p1 from this closed interval 0 1 to x1, which is connecting x1 to x1 dash, that is p1 0 is nothing but x1 and p1 1 is x1 dash. Similar to it, we can take another path, that is p2 from this closed interval 0 1 to x2 such that p2 0 is x2 and p2 1 is x2 dash. Further, it is to be noted that both p1 and p2 are continuous, that is p1 and p2 are continuous. So what exactly we have with us? Let us take, this is the closed interval 0 1 and we are having two spaces, one is x1 and one is x2. And if we are taking elements here, that is x1 and let us take this is x1 dash. If we are taking here an element x2 and let us take this is x2 dash, so we can construct a function from this closed interval 0 1 to x1 and that function is sending this 0 to x1 we are taking, and we are taking that is sending to this one at x1 dash. Similarly, this function is also sending 0 to x2 and also this is sending 1 to x2 dash. This one is we have taken, this is p1 and this is p2. What our motive is that our motive is to construct a function from this closed interval 0 1 to the set, that is x1 cross x2, and these points are here inside this x1 cross x2. The first one is x1 x2 and second is x1 dash x2 dash, and that function should come from 0 1 to this space. Question is how to construct that continuous function. Recall the idea. We have a continuous function, that is p1 from this closed interval 0 1 to x1. We also have a continuous function from this closed interval 0 1 to x2. What we can do? We can construct a function p from this closed interval 0 1 to this x1 cross x2, and how to define this function? This is sending each x in this closed interval to this ordered pair, that is p1x p2x. What we have already justified, that if p1 and p2 are continuous, this p will also be a continuous function. Also, if we are computing the value of this function at 0, that is p0, that is nothing but p1 0 p2 0, which we have already seen that this is x1 and this is x2. Similarly, if we are computing p at 1, that is p1 1 and this is p2 1, that is nothing but x1 dash x2 dash. So what we have justified? We have justified that for all elements x1 x2 and x1 dash x2 dash in x1 cross x2, there exists a continuous function p from this closed interval 0 1 to x1 cross x2, so that p0 is equal to x1 x2 and p1 is equal to x1 dash x2 dash, and therefore this space, that is the product space x1 cross x2 with product topology, is path connected. These are the references. That's all from this lecture. Thank you.